All right, last topic. We're going to finish up some of the conic section stuff. So we're really just going to look at 3 conic sections. We're going to look a little bit more at parabolas, which we already know a lot about. We didn't talk about them too much in class, but we'll look at them. We'll look at ellipses. Those are our stretched out circles, and then those hyperbolas. Those show up with those hyperbolic trig functions that we were talking about. So we'll just take a look at these 3 things, dive into the formulas of them and stuff like that, some of the properties, some of the terminology, all that kind of business. Let's start with parabolas. This is a definition for a parabola that you probably haven't seen really before. It's a set of points in a plane that are equidistant from a fixed point F, the focus, and a fixed line, the directrix. What you'll notice is that if we draw this line here, and we draw some point up here, and you want to come up with a curve where all the points on the curve are the same distance from the line to the point, or from the curve to the point and the curve to the line, sorry, you're going to end up with some sort of parabolic shape. Now, my picture wasn't very good. Maybe I'll try and do a better job. I'll go right around halfway in between. There we go. So what we're really looking for is trying to make this distance from our line up to our curve the same as the distance from our curve to our point. If you do that, you can play around with these distance formulas and all this kind of stuff. We could go ahead and say, here's a distance formula and make that equal to the distance between some line, some y value at p or whatever, all that kind of business. But what you'll notice really is that this is just going to fall out to give you this nice little formula here. X squared is equal to 4py. You could probably imagine that this looks like a parabola. If we solve this for y, we end up with y equals x squared over 4p for some value for p, and we'll figure out what p represents. And obviously this looks like a parabola that we would kind of recognize and notice. So we're going to call the focus the point 0, comma p, so that's what p is going to represent. And also this directrix, that line that we're looking at here, is going to be at a y value of negative p. So they're going to be like on opposite sides of our parabola here. And there's the equation of this thing. Notice that the sign of p, whether it's positive or negative, that's going to dictate whether this parabola opens up or down. If p is positive, then we've got a nice positive coefficient on x squared, opens up. If p is negative, opens down, just like we're used to. But we could switch around all the variables and tilt this thing on its side, too. So we have the same exact stuff, except now our focus has an x value of p and a y value of 0, and the directrix is a vertical line with x equals negative p, and we have our equation y squared equals 4px. Same kind of thing. The sign of p is going to dictate which way it opens, whether it opens to the right or to the left. Not too hard. We're not going to mess around with parabolas too much because my guess is that you've done this before in algebra classes. You've messed a lot around with parabolas. So let's just jump into this idea of an ellipse. We're going to go back to this definition of trying to define some distances with points to get this picture. So an ellipse is a set of points in a plane whose distance from 2 fixed points have a constant sum. So you can think again about a circle, and a circle is going to be equidistant from a single point. But now what we're going to say is that the distance from any point on our curve to these points, they're going to have a nice constant sum. What that means is, like, if you look at this distance and this distance added up, that's the same as this distance and this distance added up. So if you add up those 2 little line segments, you're going to get the same thing. And that length is going to be 2a. We'll figure out what that looks like in a second. So here's all the stuff about it. You're going to have 2 foci. They're at these points here. You've got 2 vertices at these points. That's the same a that we had up here. And here's your equation. I hate this equation, really, the way that our textbook writes it. I hate that they have a squared equals b squared plus c squared, because most of the time we would think that a squared plus b squared equals c squared. So you could jumble up these if you want. But for the sake of keeping constant with what our textbook is doing, this is the notation that you'll use. You'll see this, I think this is close to standard, but you'll see it with different values sometimes, different letters. No big deal. Anyways, it's a sum of squared variables divided by squared coefficients, and they're equal to 1. Notice that when we have the opposite axes stuff going on, so like here our main foci are with some x values and a y value of 0, so they're somewhere on our x-axis, and our vertices are the same. In this orientation, our foci are on the y-axis and our vertices are the same, but this looks really similar. It's really hard to tell what orientation we have because addition is commutative, so how can you tell what A and B are? The main thing to notice is that A is the big value. So really you can say whatever variable has the big value in the denominator, that's the one that dictates orientation. I know that's a little bit weird, but you'll see what I mean in a second. So here's some notes. So I think, I already said this. A is going to be bigger than B, and A is bigger than C. So whatever term has the larger denominator is the one that has the A in it, and that's the one to tell you where the foci are and all that kind of stuff. This long axis, the length 2A, is called the major axis. I think we talked about that briefly in class. And then the short axis is the minor axis, and that's going to be 2B. So B here and here are going to also kind of represent some vertices, and we're going to have a short axis that's going to be like this direction here. The value A represents the length from the focus to the vertex, and the vertex is the end of our ellipse. It's that very far edge that we'll have. So here's a quick example that we've got that we can kind of talk about. So maybe if you want, pause the video, see if you can go back to those formulas. Notice X has the bigger value. So this is going to be the one that we really use to talk about orientation. And see if you can find the vertices, find the focus, or the foci, because there's two of them, plot them, and then see if you can draw a decent little ellipse on here. I'll give you a second to figure that out, but pause the video, see if you can do that. All right, so hopefully you've done all that. If not, go back and do it. But let me type some stuff on here. So hopefully you noticed A is going to be 4, because we're really looking at this 16 right here to dictate that. You'll also notice that B then is going to be 3. And that's, again, from this value. B here is not going to be super helpful for us overall, but what it will do is say that part is going to dictate our short axis. That's pretty much all that it's going to do. And then you could go ahead and use basically like a Pythagorean theorem on here to find C, although it's a little bit annoying because it's not the real Pythagorean theorem. So we'll say C equals, let me draw this out. We're going to have a square root of A squared minus B squared, which is a square root of 16 minus 9. So we're talking root 7 here. In case you're curious, root 7 is approximately 2.65, which we'll need to know that in a little bit to actually sketch it. That's supposed to be an arrow. There we go. Anyways, so we can find our vertices now. We know that those vertices are going to be using our A values. And so let me get that a bit better. There we go. So our vertices are going to be at -4, 0. And our other one is going to be at 4, 0. So let's go ahead and plot those. If we want to plot those things, I'll need some little tick marks on here. So I'll say there's 1, 2, 3, 4. There's my first vertice, or vertex. -1, -2, -3, -4. There's my other one. This B is going to tell us our short axis. So essentially what we can say is that here's our ellipse. It's going to go through +3 on the y-axis and -3 on the y-axis. So really what you can notice is that if you just take the square root of these denominators, those are going to tell you where it crosses that specific axis. And now it's pretty easy to draw in the rest of our ellipse. We know the general shape. You guys are probably better artists than I am. Oof, oh well. Let's pretend that that's actually on there. And there's our ellipse. If you want to figure out where your foci are, that's what this C value is for. So that's going to determine our foci. So I'll just go ahead and write that in. Our two foci are going to be at -2.65. Oops, there we go. 0, and 2.65, 0. And really we could say that's root 7, right? But just for our own ease of plotting, so maybe I'll actually write that here. That's really -root 7, and that's +root 7. But I wanted to put the decimals in here so we could actually kind of plot it. That's like a little bit bigger than 2.5. So I'll say like right there, and then right there. So that's our ellipse. It's not too bad, to be honest. Figure out what these values are going to give you those are going to be your intercepts on those specific axes. So positive, -4 on your x-axis, positive, -3 on your y-axis. And then you can figure out this c by doing the root of the difference of squares, if that makes any sense. That'll tell you where your foci are. There's your ellipse. You can do tons of different things with these. You can change the values, change the orientation by changing those values. Obviously, if the denominator of y is bigger, then that means that these are going to be taller, and so our ellipse might look something like this instead. It'll be tall and skinny instead of short and wide. But cool. Hyperbolas. Hyperbolas have a lot more going on, I think. So this one is a little bit weird. It's a set of points in a... Oh, that's supposed to be plane. Whose distances from two fixed points, the foci, have, instead of a constant sum, a constant difference. So remember, let's go back to this picture that I drew. Remember how these two red lines added up to be the same as the distance between these two red lines? Instead, what we're going to say is that the difference between these two red lines is the same as this difference. And it might be positive or negative, but whatever. It's all going to be the same kind of things. So that's a bit hard to picture if you want what that looks like. You'll see it in a second, though. A hyperbola centered at the origin with foci at positive or negative c, 0, and vertices at positive or negative a, 0. And again, that's going to come from that constant difference. Here's our equation. The main thing to notice, we're subtracting here. Now, order actually really matters. So that's going to be something really interesting. This is one version. I couldn't fit it all on one page. So this is one version of a hyperbola. And then you'll notice that when we switch the order, that's going to change things a lot. So whatever term has the negative on here is going to really impact some stuff. So let's just take a look at this one first, and then we'll see what happens when we switch the order of the terms. So we've got x squared over a squared minus y squared over b squared equals 1. And b squared is equal to c squared minus a squared. Or you could say a squared plus b squared is c squared. I like these because that's the regular old Pythagorean theorem, the one that we know and love. So notice c is the big one. A and b, we can't really tell which one is going to be bigger. They could differ, but this sign, which one has the negative, is going to tell us the orientation. So you could think you've got focuses or foci on the x-axis here and vertices on the x-axis. X is the positive term. Cool. This thing has some vertical asymptotes on here. It's going to have two lines. They're going to crisscross through each other, and this is the equation of those lines. This a value is a denominator, this b value is a numerator, and then we'll look at both the positive and the negative, so we end up with two lines that look like that, and our hyperbola is going to be somewhere in between, kind of like that. Here's our other version of it. It's almost the same thing, except we switch which ones have the signs, and so notice here that our coefficients here switched, but you could really just say that the positive denominator goes on top, the negative denominator goes on the bottom. So over here, oh no, wait, shoot, never mind. It's always going to be the one with b on top. I apologize. It's always going to be the one with the y on top, and then the a is going to be on the bottom, or the one with x is going to be on the bottom. So think rise over run. Y is on top, x is on the bottom. And so whatever the denominator for the y term is going to be your numerator for the asymptotes. Whatever the denominator for your x term is going to be the denominator for your asymptotes. In both of these cases, c is the big thing, so it's hard to tell the orientation. So we'll look at the sign, and only the one set of vertices, as opposed to the ellipse, will hopefully help. So you can kind of think about where those vertices are. And again, those vertices, you'll notice here, are coming from the positive term. So really, you'll just look at whatever the positive term is. That's going to help you find some vertices, and that'll tell you the orientation of this. So let's take a look at this. Oh no, I lost my x-axis. Let me draw that back on. All right, so the positive term right off the bat on this thing is x. Oh, actually, sorry, I don't want to give it away. Pause the video. See if you can go back and fill in some information on all this stuff. Think about orientation. See if you can find your asymptotes. Give a quick sketch of what those look like. They might not be perfect, but who cares? That's all right. And then we'll go from there. All right. Hopefully we're back. So notice, like I said before, x is going to be the positive term. And so if we go back up here, we'll say, okay, our orientation is that all this stuff is on the x-axis. So we already know a little bit about what's going on then. If we look for vertices, Those vertices then are going to come from the denominator of x. So maybe first it might be helpful to write out what a and b and c are again. So a, we know, is going to be the square root of the positive term, that x term. And so we'll say, okay, that's 4. B is going to be the square root of 20. And so let me write that because I can't type it very nicely right yet. So I'll say this is root 20, which is 20 is 4 times 5, so square root of 4 times square root of 5, so that'll be 2 root 5. Approximately 4.5. So when we go ahead and like use that to plot some stuff or whatever, we'll say that's around 4.5. And then C here, we're going to say is a square root of a squared plus b squared. And so that's 16 plus 20, that's 36. That's good news for us. Square root of 36 is 6. All right, so vertices. Hopefully, we've got that the vertices are going to be using those a values. And so we've got negative 4, comma 0, and 4, comma 0. Our foci are going to be at negative 2 root 5. I'll just say negative 4.5, comma 0. And 4.5, comma 0. I've got a weird space in here I want to get rid of. There we go. And then our asymptotes we'll have to figure out. Those, if you remember, I got that mixed up for a second, but it's going to be the y coefficient denominator over the x coefficient denominator, but we're really just looking at the roots. So here, our asymptotes are going to be y equals plus or minus 2 root 5x over 4, which is approximately, that's a plus minus here, approximately plus or minus 4.5x over 4. So a tiny bit steeper than the identity y equals x. So let's draw those in afterwards. Let's go ahead and plot some points. 2, 3, 4. So there's my first vertex. Negative 1, 2, 3, 4. There's my second vertex. I'll go out another unit so I can see this half unit. That's my focus. That's my focus. I'm going to draw my asymptotes in blue. And I'm going to say, oh, this is going to be kind of hard. I'll do that. That's approximately y equals positive 1x. I'm trying to make it a little bit steeper. And then here's our negative 1. That looks pretty darn good if I say so myself. That might be even better than what I draw on the whiteboard. And then our hyperbola is going to cross through the vertex. And then we've got this nice asymptotic behavior here. So it looks something like that. And there. Not perfect, but oh well. That looks decent. And you could imagine then if we shifted the orientation and switched the signs on these, then our vertices come up here and down here. And we end up with something that looks like this instead. Let me get rid of that so it doesn't confuse you, though. So we can just kind of bounce things around that way. That's really all we've got for this. There's not much more to it, so I'm not going to waste your time and mine. It's really just kind of getting familiar with some of the little tricks about how to tell the difference between the two different forms and stuff like that. So dig into those problems in the homework. Let me know if you have any questions. Other than that, have a good rest of your day. See you, everybody.